We will be looking at two key parts, the first one being the 4 different ways to make hydrogen, and the second being the application of hydrogen fuels. With electrolysis, we will be using an electrolyzer. It consists of an anode and cathode, which are separated by an electrolyte. There are multiple kinds of electrolyzers depending on different electrolyte material. For instance, we will be introducing you to a kind of electrolyzer, which is a polymer membrane electrolyzer. As you can see, in the anode, water will be converted into oxygen and positively charged hydrogen ions. These positively charged hydrogen ions will flow to the cathode, where hydrogen ions will be converted into hydrogen gas. In general, through electrolysis, oxygen will convert into hydrogen with the expense of electricity. Why should we consider electrolysis as a method of production of hydrogen? Above all, there is no carbon emission in the process of electrolysis. However, we need to consider the source of electricity. Fossil fuels? Of course not, because with using electricity from ordinary fuels, it still causes emissions of greenhouse gases. In that case, it is necessary to consider renewable energy, like wind, solar, hydro, geothermal, or nuclear energy as the source of electricity in order to make zero greenhouse gas emissions. With thermal processes of making hydrogen, it is a high temperature process which steam will react with hydrocarbon fuel to produce hydrogen. There are many hydrocarbon fuels that can be chosen, such as natural gas, diesel, renewable liquid fuels, gasified coal, and gasified biomass. However, today we'll be introducing you to reforming of natural gas, which has taken up 95% of the production of hydrogen. In the thermal process under high temperature, natural gas, as methane, will react with steam under certain pressures using a catalyst. As a result, it will produce carbon dioxide and a lot of hydrogen. Then there is a water-gas shift. By using a catalyst, carbon dioxide will react with steam and produce carbon dioxide and hydrogen. Finally, carbon dioxide and other impurities will be removed, which left pure hydrogen. By using thermal processes, it can cost low amounts to provide hydrogen for fuel cell electric vehicles and other applications. In fuel cell electric vehiculism, the only product from the tailpipe is water vapor. With using natural gas for reforming, we can reduce nearly 50% of hydrogen gas emissions and 90% of gasoline usage compared to normal gasoline vehicles. Solar-driven processes use light to produce hydrogen. It mainly includes 3 methods, which are photobiological, photoelectrochemical, and solar thermochemical. Photobiological hydrogen production process belongs to both solar-driven processes and biological processes because it uses both microorganisms and sunlight. Photobiological processes use the natural photosynthetic activity to produce hydrogen. Some bacteria and green algae carry out photosynthesis. They can decompose water into oxygen and hydrogen ions by using sunlight. These separated hydrogen ions can be directly or indirectly made into hydrogen. Using this method to produce hydrogen is environmentally friendly and low cost, but its extremely low hydrogen production efficiency makes it difficult to become the mainstream hydrogen production method. Photoelectrochemical processes use specialized semiconductors to separate water into hydrogen and oxygen. Using this method to produce hydrogen requires immersing the semiconductor in a water-based electrolyte and decomposing water by using the energy provided by sunlight so that hydrogen and oxygen can be separated. The hydrogen decomposed from the water in this way can be directly used as energy without additional hydrogen synthesis. This method has low cost and high efficiency, but there is still room for improvement. Solar thermochemical hydrogen production uses concentrated solar energy to produce high temperature for water decomposition reaction. The high temperature generated by solar energy aggregation is used as a catalyst for this experiment. The chemicals used in the process are reused in each cycle to form a closed loop that consumes only water and produces hydrogen and oxygen. This hydrogen production method is very environmentally friendly because it produces almost no greenhouse gases. But the high temperature resistant instruments necessary in the experimental process leads to the relatively high cost of this production method. For the hydrogen fuel cell, the most basic form of cell is showed. and it is obvious to say that the important part of the cell are the electrode and electrolyte. At present, there are 5 different types of hydrogen fuel cells, including solid oxide fuel cells, direct methanol fuel cells, phosphoric acid fuel cells, proton exchange membrane fuel cells, and alkaline fuel cells. What we would like to introduce to you are the cells which use pure hydrogen as their fuel. That means hydrogen has to be one of the reactants in the overall reaction. Thus, a direct methanol fuel cell will be excluded because it needs methanol as a fuel. So let's start off with SOFC. Solid oxide fuel cell needs ceramic as an electrolyte because it's a high temperature, which is required between around 650 to 800 degrees. As a result of the high temperature, a variety of fuel could be used, and normally hydrogen and carbon monoxide act as a fuel, but it is no longer suitable for portable device and vehicles. For the polymer exchange membrane fuel cell, as the most typical fuel cell, the electrolyte are solid polymer membranes called fluorosulfonic acid. Meanwhile, a relatively low temperature is needed, around 80 degrees. Thus, it can have a relatively short starting and stopping time. The chemical reactions and processes for phosphoric acid fuel cell are similar to PEMFC, and both of them have very high efficiency and density of electric energy, which means they are suitable for vehicles. The polymer exchange membrane fuel cell had already been introduced to some of the automakers such as Toyota, Hyundai, and General Motors for making the hybrid electric vehicle. PEMFC HEV seems to be a reliable dynamic system for the future, but its durability is much lower than other dynamic systems at present. The main cause of low durability is the component called membrane electrode assembly, with short lifetime of about 1,000 hours, and it cannot reach the basic requirements for cells, which is around 5,000 hours. The alkaline fuel cell has different mechanisms. The electrolyte is alkaline metal, and hydroxide ions are conducted. The advantage of AFC is there is a wide range of pressure and temperature which can be adapted, so it can be used in several different products, including public transport systems. In the long run, it is certain that clean energy will replace traditional oil as the fuel for cars. The first hydrogen fuel cell vehicle was created in 1966. General Motors' Electrovan is widely considered to be the first use of hydrogen fuel cells to power a car. This groundbreaking design uses a fuel cell that combines supercooled liquid hydrogen and liquid oxygen. A hydrogen fuel cell is essentially a chemical reaction between hydrogen fuel and an oxidizer to generate electricity, thus converting the potential energy of the fuel into electricity. The pressurized hydrogen gas combined with oxygen in the air to form water emissions instead of the harmful emissions of traditional petroleum combustions such as sulfur, nitrogen oxides, and ozone. Hydrogen fuel cell cars will get more energy than conventional energy when the fuel mass is the same because of high energy density. Diesel has an energy density of 45.5 megajoules per kilogram, slightly lower than gasoline, which has an energy density of 45.8 megajoules per kilogram. By contrast, hydrogen has an energy density of approximately 120 megajoules per kilogram, almost 3 times more than diesel or gasoline. In electrical terms, the energy density of hydrogen is equal to 33.6 kWh of usable energy per kilo versus diesel, which only holds about 12 to 14 kilowatts per hour per kilo. What this really means is that 1 kilo of hydrogen used in a fuel cell to power an electric motor contains approximately the same energy as a gallon of diesel. Refueling a hydrogen car at a pump takes 5 minutes or less, much like refueling with gasoline. This compares to electric vehicles, which can take 6 to 8 hours for level 2 charger, the most common type currently, down to 30 minutes for the very fastest and rarer level 3 to 4 charger. Recharge times for electric cars probably will fall, but almost certainly won't be as quick as the 3 to 5 minutes of hydrogen. There are disadvantages of hydrogen fuel cells, however. The first one being that hydrogen energy is too expensive. Hydrogen will cost no less than $5 per gallon of gasoline equivalent, and in most schemes will cost far more. The second is that few places have refueling stations. There are relatively few places to refuel currently, so that hydrogen cars are currently sold in restricted states and regions, which have been known to have some hydrogen refueling stations, such as California, Germany, and Japan. Currently, there are no more than 300 refueling stations worldwide. Thank you for watching.